go through here is to show you, I put course objectives. It's not an objective for the actual course, but I want you to set the course objectives for yourself based on your knowledge level. The precast concrete is not typically taught in classrooms because the pre-stressed concrete is typically taught as a design of pre-stressed concrete classes. Precast is more or less driven by industry experience and industry engagement, short courses like what we are doing. But I think it's good to get exposed to what's happening and learn about how the industry is moving and why that industry is unique, what is that they are trying to achieve, what are their benefits. Those things would be valuable. So you're familiar with design courses. You've all done concrete design, steel design, whatnot. So you know how to do the design. So you may be, the rest of your life, just be a designer. You don't need to worry about precast. But knowing what the precast industry does will make you a better designer. You don't have to learn each and every trick what they do, but you can figure out, okay, if I do this thing, if I'm interacting with a company that focus on precast fabrication, then that's going to help you to be a better designer. So I think that should be the goal. You need to understand and appreciate. I can guarantee you that not all of you are going to be working in the precast industry. You could be a designer, but you're going to be interacting with somebody doing precast fabrication. The precast industry also focuses more so on fabrication, right? How do they make those pieces ready for assembly on site kind of thing. So there may be individuals focused only on, so if you're working for a precaster, your job, you could be, you may have a degree in civil engineering, you may be working for a precast fabricator, and they will have different expectations. So they take the design from a design firm, and then they produce their own drawings, which I'll go through more later, from which they will produce components. Once you produce the components, then you need to transport to the site. So those are the two things that once compared to cast and place construction, you design, somebody ordered the materials, you built it on site, versus when it comes to precast, it goes through a couple more steps. Engineers get involved in all of those steps. So for example, you have a multi-story building that includes a beam, which is designed to be a continuous beam. That beam could be fabricated in pieces. It could be designed as one piece, long piece, and that has to be transported. When it's transported, it could be supported in a simply supported manner. So the beam is actually going to go through a different loading than the actual continuous beam that you designed for the actual structure. So those are the things that you need to be more aware of. So if you have a structural engineering knowledge, you should be able to apply, but you have to be careful about what's happening to the process. So it's important that you understand those steps as well if you're a precaster. If you're a designer, you design them, the precaster will make sure those steps. If they're concerned, they will come back to you. I'm not quite sure how the industry operates here in India, but I'll just share some of the things that goes on based on what I've witnessed. Once these pieces are shipped to the site, the whole thing has to be assembled. So there is an erection plan somebody has to put together, and that has to be integrated in the process as well. So you design it, you fabricate, you transport, and then you erect them on site. All of these pieces, you will not be handling all four stages as an engineer. You may get involved with one or two, depending on where, what your company is focusing on or what your passion is about. So, but the reason I go through that step is I don't want you to think about, oh my God, I need to learn this, I don't understand this, how do I do this? You don't have to. But you need to be aware of it. You need to appreciate that if somebody else is going to do those steps, you need to interact with that person. So it's like, we do foundation design. structural engineers interact with geotechnical engineers to figure it out what would be the best foundation is, right? So just like that, we go through different steps. So don't be overwhelmed with the material that you're going to hear, how people are doing it. Once you have interest and expertise in one particular segment, then you will learn to interact with people working in the other spaces as well. So
in the US, I think CIA has these advanced work packages, AWP, which you guys integrate all these precast design level first.
yeah, they do, but the US practice is also more, there's a process that they centralize to help the industry. So I'll go through some as we go along here. So they kind of control everything. They bring the industry together, which is not something I believe India doesn't have established that yet.
I don't know much.
I don't think, based on what I have gathered, I don't believe India has a. So in the US, there's a Precast Prestressed Concrete Institute, or known as PCI. What they do is it's same as ACI, but they do a couple of things differently. You have to pay a membership to belong to that organization if you're an industry member. Then they also provide in return some certification, search safety training, and then they advance the research and produce design guidance. So everybody comes under that umbrella, and everybody follows a certain set of rules. There are some precasters may not be part of it, but typically, I would say in the US we have about 300 precasters are in that organization. It's across the entire country. So they actually pay membership due, I don't know, it's a 5-10 grand a year, pretty significant amount. So they pay, and then they come together and move the industry forward. I think with the precast getting more popular here in India, I would expect that, that kind of model to be established will help the industry quite a bit, actually. So when you go to this, it's a semi, like, we academics get involved, but we don't, and our goal is to advance research, but we work closely with industry. So it's a very unique setup in that they bring their industry knowledge, we bring the R&D, new ideas, new concept, and then we work together to establish what would be best practice to move forward. They can fund research if they have challenges. They have like an antitrust policy. So when they come together, they don't talk about pricing, competitiveness, nothing in that. So it's well established in that they don't compete about anything. Outside they compete, but under this umbrella, they have certain set of rules. I think it would help a great deal, given that precast is growing quite rapidly here, to establish an organization like that. And PCI, I mean, you can certainly establish some kind of a association with the PCI in the US for sure as well. I believe they have some association with companies in the Middle East, for example. So somebody has to take a lead on that. So yesterday you talked about, I think Professor Amalan talked about pre-stressing. So that's something that you need to realize, that pre-stressing is a very integral part of precast fabrication. Pre-stressing gets used quite a bit in the precast world. And pre-stressing is something unique that actually uplifted this particular industry as well. So the material properties of pre-stressing wires and what we take advantage, I don't know how much you covered, but it's important that you learn those things as you go along. The next point I want to mention under like setting your objectives is a very common mistake that people make is that when they do, so you know how to design a structure. Then to build it, you can do a cast in place. You just build it in place, right? You're familiar with that. And then you say, okay, I could do it differently. I'll go with the precast operation. So up until about 20 years or so ago, what the thinking had been is that you know how cast in place concrete works, whether it's a column attached to the foundation, wall attached to the foundation, or the beam attached to the column. And the expectation was that I believe I shared a art paper. I don't know if where's Virendra is here. So he will, if he hasn't, he will give you a copy of that paper. What people have done up until then is that they would force the precast structure to behave just like cast in place structure, which is, people just didn't realize until recently that's a bad thing, right? I mean, precast has some unique properties. Maybe we should take advantage of it. Maybe we should not force it to behave something it wasn't built that way. When you go away from that, you start to realize that you can actually come up with some innovation that would uniquely promote precast concrete, but also promote better performance, better behavior for precast structures as well. So that thinking has been now coming in more and more. So don't look back and say, okay, I know how, if I push on a column that attaches to the foundation, I know how it works in a cast in place. Then you have a precast concrete and you try to do the same thing. And there are ways to emulate, that's where the emulation terminology came in. You try to emulate, force it to behave like that. People did overlook some issues that has seen, for example, in earthquake situations, it's shown to be performing differently than cast in place. Then people were wondering why that happened. Because we force it to do that, right? So we'll talk more about that quite a bit. So you probably have heard about ultra-high performance concrete. The same thing applies, right? I mean, ultra-high performance is going into the cast-in-place world as well as precast world. And ultra-high performance itself has its unique properties. So you don't design something out of ultra-high performance and expect it to behave like a cast-in-place. It's not. Because if you do that, you won't create a cost-effective system, and the owner or whoever paid the bill will say, it's too expensive for me. So you got to change, you got to pivot and see, how do I design it because I have these new properties for this material, construction practice, and so on. So the last bullet I included here is the understand your role. So that's what I kind of emphasized at the beginning. So if your passion is about design, the key would be to how do you interact with the precast fabricator. So there are companies, consulting firms specialize in precast structures. They will design and work with precasters. And occasionally you will have precast companies will also have a division focused on actual design of structures. Especially for some unique structures like that, they will have the capabilities. So it sounds reasonable? Any questions? Either I'm not making sense, or you're not understanding, or you understood everything. So,
in India, most of the companies I know, they provide design and services.
Okay.
They have an in-house design team.
Right. Yeah, I think the growth has to come, then things will come in. So for example, in some parts of China, now you cannot build cast-in-place concrete because of the environmental factors and things like that. They have to do prefabrication. So once you force, then every consulting firm has to kind of fit into that, basically. Any other question, comments? Okay, so the first topic I wanted to talk about is total precast system. So when you say prefabrication, we think in terms of building a beam offsite or building a column offsite. In the US, the trend has been more moving towards what they call a total precast system. So they design the entire structure out of precast products. The reason they do it, they claim that it's cost effective. They can do, so the on-site labor is more expensive, maintaining quality on-site is challenging. By doing something like total precast, you can do a lot of wonderful things as well. So I put together a set of topics to cover here in terms of what total precast looked like. So I want to just talk about the total precast, some historical perspective, and then I'll go through different topics real quickly. So the total precast construction basically uses precast concrete elements for all major structural components. So typically precast will rely heavily on walls and precast floors. That's a very common practice. Walls and floors are easier to build. They can be easily transported and just put them together fairly easily. So if you think of a square building, it's much easier to come up with the design, build, put pieces together, and complete the structure itself. It doesn't mean that they will not use some cast-in-place concrete. So sometimes they will use some small amount of cast-in-place concrete. They will use grout. They may weld pieces. I think in recent time they are starting to use UHPC. Typically all components are manufactured off-site. So the reason I put that is you need to realize that. So if you have a job site and you have a prefabricator, every component has to be transported, right? So what road conditions you have matters in terms of how long the pieces can be. Ideally, you want to keep the pieces as long, as big as possible. So two things come into play. One is the weight. The second piece is the length. So there are restrictions in terms of how long of a piece that you can typically transport. So if you go about 10, 12 meters, then you have to get special permits from the highway system. And then once you go 12, then you have to have what they call an escort vehicle. So you have to have a vehicle in front telling, hey, there's a big load coming behind me. There's a escort vehicle behind. But they do that sometimes, but they add cost, right? So the moment you have to have escort vehicles, the cost of the component that you're transporting increases significantly, right? So you cannot just design and think of, okay, they can make this big piece and transport it. They have done some long piece transportation, so they sometimes use barges to transport pieces. Recently I've seen somebody design, it's not built, 100-meter long piece. Well, can they transport it? So it depends on, how do they get there? So sometimes what they do is in those cases, they may cast it on site, but still as a precast component. So they prefabricate it and then erect it and put it in place. I think Satish Jain is coming. He's done some building structures like that with the UHPC, where he cast pieces and maybe he will show those things. The third item I put in is what's the most critical thing that comes to your mind based on what you heard so far?
Logistics.
Yeah, logistic is one. So you can see how people are thinking, right? Logistic is a one main challenge that comes in. What else?
Connection.
The connection is a huge piece, right? You can't cast everything as big and nice or small. But when it comes to precast, connections. That dictates how will the structure perform. So the connection design has to be very strong in terms of, when I say strong, I should say maybe it should be more robust in terms of how well the connection is designed. So when you take each and every precast member, they themselves can satisfy all of your design requirements. But if the connection doesn't transfer loads or provide resistance, then the structure will fail. The components are going to be fine. So the connection is a big piece of the puzzle. And then obviously logistic is the other piece when it comes to transporting components. So logistic dictates the pieces and then actual the connection details. So you should always, if the moment precaster comes and talks to you as a designer, you should be thinking about the connection piece. So let's just think of a simple thing. Just you're designing a simply supported beam. It's a long beam, but the precaster say, I need to cut this into two pieces. So the reinforcement that you put into the beam may not be working for these two pieces that you're now going to be casting it. Now you have to bring them onto the site, and remember that those two pieces are going to be lifted as simply supported pieces. But you didn't design them to be simply supported. You have a long, big piece. But the stresses the beam is going to see is going to be very different after you cut into pieces. Now, once you bring it to the side, you're going to connect the pieces together. So the connection has to be strong enough so that it acts as the long beam that you design. So you kind of get the feel for how these things have to, come together. When you have structures like that, so here's a structure, it doesn't have a lot of openings, so when you don't have any openings, it's very common to see wall panels and floor slabs. So in this case, I don't know if you can see, is that a pointer?
Yeah, that's true.
Okay, so you can see these are wall panels. These are wall panels with openings. These are what they call a hollow core planks going in that direction. These planks are going in this direction. So you design the entire structure. When the structure is exposed to a set of loads, wind loads and live loads and gravity loads, the entire structure has to be resisting those loads. I mean, that's what you start the design with, right? You have an entire structure that you're designing for. But now these pieces have to work together. They should be connected sufficiently so that it acts as a structure. So that's where the connection becomes so important. And so in this particular buildings, they use hollow core floor plans as well as the wall panels to ensure some sound resistance. That was a requirement. So that went into, so somebody comes and say, I want to design this. We have machinery is going to be making noise. This would be an ideal structure to use. The hollow core panels will also support sound as a sound barrier. So you can see how they would be thinking of bringing this structure together. So you don't want to just go and start designing. Somebody wanted a structure of this, you need to have that expectation in terms of what they're looking for. And if you are thinking of precast structures, then you want to choose the elements to do that. So if you don't have a lot of opening, like you have a apartment building with a lot of windows and things like that, it's very common to see wall structures or wall panels get integrated into the precast structures because they are pretty cost effective in terms of resisting loads as well as providing some other functional needs as well. So there's a historical perspective. Precast industry is not very old. The first ever precast structure was built in 1950 in the US. It was a bridge that was built. They tried this as a prefabrication because there were a few people who was keen on pushing this idea of doing things off-site and then assembling it on-site. Those few people felt so good after the construction and the success of the story, they thought they should just come together and share their ideas and build a movement behind this prefabrication concept. And that's how the precast industry actually started in the US. It's not a lot of companies came together. It's like a handful of engineers felt so good about what they have achieved. They thought we should create some design guidance and put different ideas together. So they sat around the table and said, maybe we should try this. And so that's how they started, and then start publishing what they call some handbook ideas, where they will put some ideas and say, okay, everybody should use this idea. And I'll get into why they went that direction. And at the end, what you find is that 4 or 5 members that invested energy is what today is PCI. Then they brought more and more people and built the industry. So it took 75 years. Now it's a several billion-dollar industry now in the US in terms of what they produce. I think that's what I see here in India, that you don't have an organization. So if it's a concrete organization, they tend to be more biased towards cast in place because they get other, so the investment come from like a concrete cement producers, concrete mixed design companies, because they make money fairly easily. They can throw this money and control things. So the precast kind of get left out. So now that they built that momentum in the US, now they are negotiating with ACI, for example. The American Concrete Institute used to control everything for cast in place. Now they are kind of trying to be equal partners. That's one of the reasons that 319 has been now published.
The main thing is also they look at only the initial cost.
Yeah, correct. Yeah, yeah. I think the value of precast is also not appreciated. I think as much as it should be. And I'll show you some of the things that they have done in the US. So if you look back at the growth as to why the precast concrete industry grew faster in the US, obviously you will find that the speed matters. They can build these structures faster. I'm more familiar with precast use in bridges. We used to build bridges for over 6 months, 8 months. Now we're talking about assembling things within a week. We come up with the idea, work with the Department of Transportation, and we say, okay, we can do it in a week. Then 2 days later, they call and say, can you do it in 2 days? I mean, that's where things are now in the US when it comes to the prefabrication assembly. They're not looking for a, super long, curved, 12-lane bridges. For simple structures, their goal is can we build it in 2 days or a weekend, or get the pieces in place so that traffic doesn't get disturbed, and then you continue to build whatever you need to do, right? So that's an accelerated bridge construction concept has grown so much. Almost every bridge now is looking at how to accelerate construction.
So the Tacoma Bridge that collapsed and the Mississippi Bridge that collapsed, they were of precast concrete?
No. Those are, the Tacoma Bridge is a steel structure, with obviously deck is a concrete planks, I believe. But it's initiated by vibration-related issues, right? So it's nothing to do with, yeah. But I'll talk about it maybe in a couple of days' time. But a lot of the precast building did suffer damage in earthquakes. So that was a big, a negative for precast industry. That's how I got involved with the precast world as well. So obviously it's widely used in the US as well as in Europe. In Europe, certain countries use precast a lot more than other countries. For example, Italy used quite a bit of precast fabrications. So it's country dependent, but they definitely using more and more. Middle East has picked up quite a bit in terms of precast fabrication because they have a weather problem also, right? So cast in place construction is not always easy throughout the year, so the precast is obviously easier to manage. But certainly in Asia, it's good to see, China and India are starting to use more and more. I think it's two of the leading countries in terms of, infrastructure build up these days. So I just don't want to paint a rosy picture about precast concrete. Just like any other technology or material, precast is also have its own challenges and limitations. The first thing is the transportation and handling logistic. We talked about that, right? So every piece has to be transported, as well as they need to be handled. So when I say handling logistic is in terms of understanding, how do you transport each pieces from fabrication to the job site. You will find that some design flexibility limitation because you're breaking them into pieces. So for example, under seismic provisions, you're expected to have members to have sufficient ductility. So if you're going to connect pieces, will that affect the performance? If so, how do you tackle that piece? Or should I not use that one? So precast is not widely used in seismic, But there is some small growth in that space as well. So there needs to be coordination between the design firm as well as the manufacturing or precast firm. But those coordinations are, like in the US, is done pretty well, because a designer, when they do the design, if they think it's going to be a precast building, they would already have a precasters on board, either as a consultant, or they will have them as part of their design team. So they kind of integrate that relationship from the beginning to eliminate these challenges as well.
These highways, they have height sensors. So they give the height sensors in advance to the precast. So they say it should be less than that.
Correct, yeah.
So
So typically in the US is about, I think 3.4 meters is the limit. So anything that exceeds, and the lengthwise is about 10 or 12 meters. Again, you can transport if it's possible. Barge is one, so if you can transport through the waterways is a possibility. But those things add cost. It's not like putting it in a semi and take it to the side. They would prefer to do that operation if possible. The initial cost comes in because they want to maintain quality. So for example, they use steel foams typically. So that's why the product comes out to be pretty good in terms of the dimensions, the finishes. So precasters would prefer to use steel foams. Steel foam requires money, obviously, so you need to have an initial investment. So some of the products like a double T's or floor slabs, they will standardize everything, so they can produce them to any length and certain length, and let people pick which size they want to use. They do have specialized structures. Sometimes, they may have only one or two components that they have to produce. In those cases, they will probably use a timber foam. The steel foams will be very expensive at that point. But when they do a timber foam, still they do a pretty good workmanship to make sure the quality comes out pretty good as well. And you will find that precasters are pretty creative in terms of influencing the designers up front, so that they try to bring in more and more repetitive products into their construction design and things like that. So if they buy a steel foam and produce 100 pieces, that for them is a pretty good deal. And typically the precast factories are runs on a 24-hour cycle. So in other words, they will come in the morning, like 4 in the morning, come and start producing, build the pieces, cast the concrete. It's not just one crew, they will have multiple crew doing things. The next morning, 4 o'clock, the bed will be cleared, and the next crew will just start building the next piece. So they run them efficiently and faster in terms of making this production faster. So one of the roadblock for UHPC is that the curing time or heat treatment kind of delays things, and that tend to cause some challenges as well. So these are typical components that people can mix and match. The dimensions are typically standardized. If you can use a standardized dimension, they would welcome that. When I say standardized products, they already have formwork for that. And so not every precaster will produce every member type out there. Some focus on only bridge girders. Some only do wall panels and double T's. Some will do hollow core only. Some will do piles and columns. So if you are going to do precast structures, you can just buy products from different companies, and they provide specifications, and from which they get the pieces. The logistic part will come into play. So this is the role of the erector, and they will schedule everything as to which day the component has to show up to the site. And if they don't produce this, provide the components on site by the certain dates, they get penalized. So everybody kind of works towards making this happen in a timely fashion. I mean, they could assemble a building like a 5-story within like 3-4 days once the foundation is done. I mean, they move pretty fast once they get things going. So I mentioned that the precast will go through a 24-hour cycle. So you could see what goes on to that 24-hour cycle. So I kind of talk about the entire manufacturing process. Here you have the design and engineering work is done first, right? So that gets transported. Then the mold is prepared, reinforcement is placed. So typically they will assemble the reinforcement. They will have different crews doing different things. One crew will be preparing the mold. One crew will be assemble the reinforcement. Then the reinforcement is get put in place. I think Satya Seelan is supposed to talk this afternoon. Maybe he'll show some of the process that they go through here. And then they will cast the concrete. So typically, at least in the US, by anywhere from 12 to 2, they would cast the concrete. That's the sweet spot to complete the construction. So that's the window they have, and everybody work towards that time slot. After 2 o'clock, I think one crew will leave, the other crew will come and, sometime they will put a burlap or like a sack, with a wet, if needed. Then they will begin to set it up so that they will do a steam curing overnight. And the steam curing is done, so in the early morning there will be one of the crew member will show up at 3 o'clock and start breaking cylinders to see. These cylinders are cast on site. They would have thermocouple going into the precast product and make sure that the concrete cylinder get the same temperature. So they maintain the temperature, they cure it, they break the cylinder. At 3:30 they know it's good to go, and then they'll strip the foam, and then they will basically move it out of the bed. And at that point they can decide when to transport to the site. So typically they will, if you design a building, precast is involved. The site has to go through a lot of preparation, right? You have to do the foundation issue is there, utility need to be put in. So during that time frame, the precaster will start building pieces. So by the time the assembly is ready, they would have cast more than 50% of the products. And all they have to do is they have to logistically transport the pieces to the site so that they get put in place in an efficient manner. So erecting the structure is also not easy. You can't just go and put pieces together on your own. It has to be thought through. So there will be a separate crew actually go through that process, because the structural members will see different loads during that time. So you need to figure it out how to support, how to brace, how to, how much load it can take when it's supported. Will it require temporary shoring? So if you require grouting, if you require in situ concrete, if you require establishing coupling using couplers and things like that, most of the time they don't actually do that during the erection. They erect the entire building, and then that crew will go, and then another crew will come and just establish the connections per requirement. So the structure has to stand on its own during that process as well. So those things also had to be designed and checked to make sure that there won't be, wind blows and the building comes down kind of thing, right? It has to sustain some loads during the construction as well. Any questions? Yeah.
The major the constraint of adoption precast, especially in city areas, is the lack of accessibility for erecting.
Accessibility for erection. Okay.
Erection is a big, especially in the city areas.
Okay. So one of the things in the US is that not all, but some precasters would have a crew doing the erection, but most of them actually have a separate company will do the erection, and they design, they specialize, and you give them any challenges, they will make it happen because that's what they specialize in, right? And sometimes they get involved and say, okay, that's too big of a piece. You give it to us in 2 pieces and it design a connection. So yeah, like especially with you have existing structures like strengthening type of things. Yeah, they go through those things quite a bit. Any other question, comments?
Because also another reason why the UHPC and Iceland concrete is picking traction here is, as you know, the boom height, the weight that you can lift is also
correct, lower.
limitations. So that's another reason why the precasters are really looking at Iceland concrete.
Oh, I see.
The crane demand is also very high. You don't find cranes, and crane operators finding them is very difficult.
Oh, I see. Yeah. Yeah, I mean that's So these like again, you had to have enough, footprint to be able to have a decent size. So in the U.S., it's easy to find 100-ton cranes. You go past that limit, then it becomes a challenge. So when you get precast involved in small bridges, small building, they will insist on the weight limit as well, so that you don't run into, waiting for a crane or it comes from another place. I mean, some of the constructions, they use very heavy crane. I think the largest crane in the US there's only two cranes in the country. And so for example, in wind turbine tower construction, they use them. And they charge about $500,000 to just bring the crane to your site. So it's an expensive thing. So the smaller the crane, the better opportunities that you're going to have, better ways to save money. But then you also end up with more connections. So we're just finishing a project for California Department of Transportation. They put in limit on weight as well as the length. And because they said we go into terrain where we cannot deploy big cranes, but we don't want to have too many connections either. So we ended up actually mixing and matching some with the high strength concrete, some with the UHPC to produce a member that would satisfy their need. Okay, so I just want you to understand how we talk about what the sequence is. If you're a consulting engineer, you're designing a structure, you probably have seen engineering drawings that comes out of they put the beam sizes, beam dimension, how much reinforcement is needed, what's the size of the reinforcement. People don't build structures with that drawing. All it tells you is it's basically what's required in the structure. If you give it to a precaster, they will create what's known as a shop drawing. The shop drawing produces dimensions, formwork requirements, any embedment that goes into the structure, the amount of rebar. They will get it down to the numbers so that it gets ordered, it gets delivered to the site, so that the crew building it has everything what they need. There won't be anything excess, or there won't be any shortage. They need to have every piece. Where does the embedment goes? What's the embedment detail? Who produced the embedment? All of that gets produced by through the shop drawings. That's what they communicate. So they take the engineering drawing and they will produce a shop drawing. Shop drawing is what gets used in the actual production. And everything will meet what's required in the shop drawing. So as soon as the shop drawing gets produced, there may be some plates needs to be embedded in the concrete because design called for some connection that requires welding, so they embed plates. If you're embedding plates, it needs to have shear studs on one side, for example. Then those things all basically comes out of the shop drawing, and that goes to a different shop to produce all of the embedment. Those guys should be completing those production before precaster can start, building the foam, because they only have 24 hours to do everything, right? So they go through a very fine logistical detail to make sure that nobody waits on another person. Again, you're improving efficiency by cut down the time one waits for the components to come. While the shop drawing does this, an erector will go through what they call an erection drawing. And they will produce another set of drawing, and that's what goes with them, with the precast product to the side. will tell you how to temporarily support the elements. Because if you don't support it, they have concern about stability, it may crack. So again, at the beginning I said, don't think, oh my God, this is crazy, I shouldn't be getting into this. I should go and do steel structures or something. I just want you to think, you're not going to get involved with all aspects of it. But you want to know that this is how it's done. So what you produce is not, as a designer, does not get used to actually erect the building. There will be erection drawing, and there need to be checks and balances done to make sure that nothing goes wrong during the erection so that structure is not compromised. So for example, you design a beam to be crack-free under service load. During the erection, you don't want to see any crack develop. So if you don't do a proper job, you may cause cracking in the structure. That will remain forever, even though you designed the structure to be crack-free during its service, under service load. So, the erector know what your expectations are. They do the numbers. They will put additional support. If they have concern, they will come back to the designer and say, hey, there's no way I can maintain crack-free member. Is it okay if I temporarily support this? It's very common to put temporary supports in, they will establish very simple thing. I'll show some details. Fairly easy to establish temporary support into the precast concrete members. And then they will they patch up the holes if there was one, and you won't see it anything. But all of that has to go through in order to complete the structure.
So actually QA/QC, which plays a very important role before we can issue for construction.
Right, quality control happens actually in the production side as well as on the erection.
From drawings to assembly.
Yeah, definitely, it happens in each stage. So they will have they are specialized in those things. So for example, if you're doing welding, if you're doing grouting, or everything gets inspected, they need to qualify those things as they meet the expectation. They need to produce strength, they need to make sure the weld meets the standards and things like that.
You have a session on that.
Oh, so yeah, very good. So on the design side, you basically will do your structural analysis for load-bearing capacity. One of the things that is growing significantly in the US is architectural feasibility or flexibility that they will explore. So precast would push this idea. If you have let's say you have some kind of a fancy faces outward looking, some texture, they could build them in place. If you want to use color concrete, you can use them. So there are things that some architectural thing will be very unique. They can make it work for you. So those things have to be dealt with up front because sometimes that may increase the member dimensions. So the designer needs to be aware of that as well. Often they tend to work with what the dimension that designer provided, but the architectural flexibility does come into play as well. The other thing the precasters do pretty efficiently is integration of mechanical and electrical system. They don't allow you to put holes into the floors and things like that. So anything that you need has to be designed in previously, and they will embed, anchor points. So you want the holes on the floor slab to get the duct through. All of that has to be integrated. So the mechanical so when precasters get involved, the building gets, by the time they assemble, each crew will come and put their pieces and the building will get completed pretty good. In some cases I've seen, if it's a tall structures, there was a building, 39-story built in San Francisco, I don't know, it's in the high seismic zone. San Francisco is it's like Mumbai, right? It's a high real estate. So the structure got built first, and then the architectural pieces and the mechanical things done from the floor down all the way to the top. As soon as they're done with the 5th floor, people started occupying while they're building the rest of the 34 stories. So, because they can start paying the rent, right? So if you tell them that this involves money, they will make it happen. The fire resistant, I think hopefully you will hear from some of the fire resistance is a key piece that precasters try to take advantage. They believe that they can provide better fire resistance than, say, steel structures. And if you want to have any fire coating, any specialized provisions, they can actually integrate them as well. And then on the durability side is also one of the reasons the precast get used is, I think I may have something, it provides better quality. They minimize water leakage and things like that so that it prevents unnecessary maintenance. They maintain the structures pretty well over time. On the structural performance side, high strength and durability. So the durability is a key piece here. Strength-wise, you will find that most materials, I'll talk a little bit more on the next set of slides, that they will use higher strength concrete, higher strength, the strands is very high strength. Rebar is also now they're pushing towards higher strength rebar because anytime they can put less amount of reinforcement, it basically cut down the labor, it translates to saving. So they look at every step of the way. The consistent quality due to controlled manufacturing. So once these members are produced under controlled environment, as I said, they use steel bed, steel formwork. They use thermal curing. So if they're producing like 40 pieces, they can actually make sure the quality of each and every product is the same. They can crank the temperature if it's a cold day and continue to improve the performance as well. They have done a lot of work in the recent years to show that it can provide better seismic as well as fire resistance. It's probably two areas that PCI is continuing to invest more. Efficient load transfer between elements. So this is again coming down to how do you connect column to the floor. In the cast in place world, we typically run the reinforcement, but precast opens up a lot more opportunity, especially with the recent the research that has happened in the last 20 years. Mentioned connections, we'll spend more time on that some more as well. So construction sequence, as a designer, you probably have been familiar with how you do the structural design. You figure out the load on the structure, and then you basically figure out the loads on individual members, and you design the reinforcement and the dimensions and things like that when it comes to design. Obviously, when you build, it goes from the ground up, right? So the construction sequence has to obviously address the site preparation and foundation. And again, very rarely they use precast foundation. Sometimes they use, but typically they don't use precast foundation. They're typically cast in place. But once that schedule as to what the foundation construction is, then the delivery of precast elements will be scheduled. Crane erection assembly sequence will be scheduled as well. So everything has to be done in a manner that nobody in the critical path causes any delays. They don't wait for somebody else to ship some piece or there's a piece missing. They don't kind of start the project until they give an okay by the foreman from each plant, especially if they have working with multiple precast plant. The joint finishing, I think I mentioned that all of the joint, if it's a finishing required like grouting, that happens at the end. So the precast industry argue that the faster construction, that's for sure. You don't build formwork, you move the formwork to the next level. None of that takes place, right? So months can be reduced to weeks. Weeks can be reduced to days. But a lot of work happens off-site in prefabrication. I emphasize the quality improvement. The labor, so typically in the US, I don't know about here, what they call a shop labor, where you work in a precast factory, is cheaper than on-site labor. And on-site labor also cause injuries. There are deaths happen because somebody fell or somebody got hit by a vehicle if it's a building a bridge and things like that. So they promote those things as a positive things towards time. Okay, 5 minutes, okay.
You can take that.
Yeah, I'll continue after that. The waste has become a big component now, right, in terms of how much can you minimize in terms of waste. So Precast do a pretty good job in terms of minimizing waste. They recycle a lot of the leftover concrete and things like that. So they definitely minimize the amount of waste as well. I talk about safety and the sustainability is the other piece that they are promoting more and more. So they're trying to bring in sustainability in a number of different ways, either in the production of the members. You've heard of the LEED certification. I don't know, is the LEED certification common here or something equivalent?
There is an equivalent pre-heart,
Okay.
IHA.
Okay.
But LEED is also
You can do here.
it is being practiced.
So they play into those expectations to improve whether they save time, cut down the carbon emission, things like that.
There are two agencies. One is the GREHA, as Mr. said. Another one is the IGBC.
Oh, okay.
IGBC is the authorized vendor of LEED, like what you
Oh, I see. On behalf of LEED.
Most of the government projects are done by GREHA,
Oh, I see.
but the private fellows they go to IGBC.
LEED, oh, I see.
They also have a certification for products as well.
Yeah, they have material circularity.
Oh, I see.
Circular economy that they promote. With the material circularity.
Okay. Yeah, so briefly, the cost issue, we talked about that, right? There's an upfront cost, but definitely saving in labor and construction time. And so one of the things that US has also not done well, but they are spending more and more effort is to bring a life cycle cost analysis into the structural evaluation so that they can promote precast fabrication. I think, I don't know how much the life cycle cost is given consideration here. No, yeah, so, yeah. Yeah, I think that, yeah, so that's a big piece. I mean, the UHPC world also kind of struggling because life cycle cost is not given that much consideration. But industry is putting a lot of effort in terms of making that happen. Why don't we take I've got like 2 or 3 slides and then I want to give you some examples. Why don't we take a break now?
Yeah, we can take 10 minutes.
Okay,
So I've got one question.
sure, yeah.
You mentioned about this Precast Concrete Association, professional association. Do they sell designs for design standardization?
So what they have done up until now is they put out a design handbook, which on the next section I'll talk about it. But in the last, I would say 5 years or so, they felt like, so the building design in the US is controlled by American Concrete Institute, the ACI 318, right? So the precast industry said, why can't we just establish our design and put out for precast, which ACI didn't like it because ACI has, for example, pre-stressed concrete is covered in ACI. So there was a little bit of political war went on for a few months. Finally, ACI convinced PCI to come and work with them, and then they will produce design standard one for cast in place concrete, one for precast related. Then we also have a post-tension institute in the US, PTI. They said, well, why are you leaving us out? So now they have a document on post-tensioning as well. So 318 has been now replaced with 318, 319, and 320. So the first version is out now in 2025. So you can get 319 and 318. There's still kind of, few issues here and there. But so they're going to promote all three now. And yeah, it's one of those things in the design codes. In any country, I've never seen it shrinking over time. It just grows.
It goes more and more.
Yeah, if you look at an ACI code back in 1950, it's like a thin book. That's how it should be.
Well, we have also done the same thing for IS-1.
Yeah, I imagine, yeah. All right, let's take a break and then we'll come back.
Here, typically, as I just told, that the design.
So we talked about various things. I think the last item was cost issue. I mentioned that sustainability and resilience is something that Precast are thriving towards. They want to promote this as a material that will promote sustainability as well as resilience. As I mentioned, that they do use reduce the amount of waste during constructions. They minimize the energy use now. That's another thing that they are paying attention to. They use recycled materials, I mentioned before. They have done quite a bit of work in the recent time to make the structures more resilient towards earthquakes and extreme wind loads. And then we talked about the LEED and green building certification. So typically precasters tend to promote that idea that they can help building owners achieve those certifications as well. So if you look at the applications of precast concrete, they pretty much use the concept in almost in every industry sector. So it could be commercial, it could be industrial. Very common to see a lot of warehouses are built from, warehouses typically have wall panels and a rooftop. And so that's very common in almost in every country that they use warehouses out of precast concrete. Another popular structure is parking garages. Certainly in the US, almost every parking garage that gets built is made out of precast concrete. They do schools, hospitals, malls, stadiums. They're going into all sorts of various type of structures. Again, to be successful, what they need to be doing is that they need to be producing the same components again and again, right? That's a key. And they make the structures more architecturally appealing. So combination of that tend to attract owners as well. So I want to go and show you some examples of what the industry has done. This is a parking structure. So you could see they already put some architectural features into it. So when they ship these components to the site, the architectural features that you're seeing here, these things are already built into the members. So that when you assemble, you basically have the structure. So there's no additional work required to put these architectural features onto the structure itself. So that's very, very common thing as well. I've included this slide to show you the fact that this is a floor slab, double T floor. You could see that they're using steel foam. So this is made out of steel and the foam is permanently built in. They can manipulate how much pre-stressing to put, how long of the bed how long of the piece to build. But typically they would standardize and keep producing the same member again and again. You could also look at and appreciate the quality of finish in terms of, so these are very thin members, so you don't want to have dimensions varying within that thin member. So if you look at the top flange, the dimensions are pretty accurate. Because it's a steel foam, the dimensions as well as this cutout that's used for supporting on beams and things like that are done almost to the dimension that the designer called for. What do you see in this particular structure? There's a lot of repetition, so they have like 4 different wings. What do you think what this structure is? It's a prison. It's a prison.
Prison.
Yeah. So the two things that precasters have taken advantage. One is there are 4 units, so anything they do in one unit actually goes into every wing that they have. Because prison has a lot of cells, if you may imagine. So all of the cells are built in already. So when they assembled, all of the cells are in place. And it doesn't look like a bad structure, right? In terms of how they integrate architecture, and people who are inside don't see the outside, but at least people outside can appreciate the architecture of the structure as well, right? So you could see in the next one, these are gravity columns. So these are all columns, and you could see how they built in the architectural features on the front of the structure. So these are regular structures, but they are load-bearing structures, but the architectural piece is integrated into it pretty creatively. So these are the things that attract people when they see structures like this, very unique. They can repeat these things once they develop the formwork for one particular structure. So this has a lot of openings, so they relied on more of a beam column type of details. You could see that architect created some kind of a curved front face to the structure. Hopefully you can see that. But if you look at individual members, there are many of them are same members, same regular dimensions, and there are a few of them are curved. But if you look at within each piece, those are not necessarily curved, but the structure itself is curving, right? So those are the things that have to go through. You don't come up with a structure where each member has a different dimension and different curvature. That's a nightmare. That's not something that you will save money. So getting them involved up front is very, very valuable. Here's the front of a structure. Again, this is precast. I included this. If you look at the top floor or the upper part of the structure, you see masonry. So it's not actually masonry. What they use is a thin brick. Do you guys use here? So thin brick is about, I would say, 1, 8 is 3. So it's about 8-9 millimeter thick brick element. They put them, so they have a standard practice where they put it on the bottom of the form. They pour concrete, and the brick basically get attached to the concrete itself. So if you lift it up, it looks like a brick structure. So if somebody wants their structure to look like a brick structure, they will actually create this thin brick elements integrated into the concrete columns or walls. So it's very common in the US to see this kind of thin brick. They can do it in any color. They could have some textures going horizontally or vertically, name it, they can produce them. Here is the precast structures which require a lot of openings. So in this case, it's all designed with the beams and columns. Again, pay attention to, if you focus on each and every members, they're not really curved or anything difficult. So any curvature that you see, they would have repeated for every member so that the formwork gets repeated rather than a unique formwork requiring for each and every member. So anything that architecture come up with his or her vision, you then turn it into something that you can fabricate. So when the precaster comes in, they will say, if you do it this way, you will save $3 million. Everybody listen. But you got to have that ability to put that on the table so that it's an attractive feature in terms of saving as well. This is an apartment building. It's a pretty uniform structure, but look at how well the building looked after they completed the assembly. They didn't do any painting, they didn't do anything after building is built. It just got built in place with all of the architectural features integrated, and so this is the type of structures that they will be working on some floors up in the upper level, whereas people can occupy the lower level because everything gets built. So all of the ductwork is in place. All they have to do is establish connections for fiber optic, electrical, and things like that to be able to complete it. This is a large storage tank. So one of the successful use of precast pre-stressed concrete in the 70s was actually building water tanks. And you can see this is a massive structure, and they're using, it's a curved structure, but if you look at the curved shell, each shell has the same curvature as well. So again, they just have one formwork. They will keep repeating it and produce the components as required for the structure. The other thing I want you to focus is that how the erector came up with how to support the structure in place. So these are each pieces get supported, and you can see between the panels they have a cast in place concrete basically establishes a joint between them. It's basically that joint is, so they have vertical pre-tensioning in each of the panels so that they can go fairly larger height. So there's vertical pre-tensioning here. Then they put this concrete in between the panels so that they come in full contact between the two. And then the horizontal connection is actually established using post-tensioning going through those ones. So they basically compress the whole thing and keep the entire tank compressed so that it remains crack-free. So pretty creative in terms of how the structure was conceptualized to how they were finishing the design. So in this case, whoever is doing the erection has to go through and make sure that they can support each and every element and then maintain stability of it as well during the, so they account for the wind loads. They don't necessarily design them for seismic, but they account for the fact that if a small shaking happens, they shouldn't be falling into pieces as well.
I'm just curious, how do they pass the strands through those?
So they have actually
Machines?
yeah, they do have a technology. So basically they run a cable through and a machine will pull the cable out. I think what I heard is they can pull cables for like 300, 400 meters. The post-tensioning will basically have established their capability as well. Yeah, so one of the things to realize is the post-tensioning world has also advanced their technology. So the strands are more reliable. They tend to, they can protect them from corrosion and things like that. Still happens, but you have to take some precautionary measure. The anchors themselves are pretty reliable these days compared to how it was 20, 30 years ago. And they have high strength as well. So they can pass through bundles of them. So I think your homework assignment yesterday, you included 8, I believe, strands. I've seen as much as 30, 50, 60 strands that they can pass it through and apply post-tensioning. How many of you know this building? Huh? What's that? Anybody knows where this structure is? Santa Ana? What?
San Diego. In San Diego.
No, it's not San Diego. Yeah, it's the Apple campus. So this was completed in 2017. So this actually used heavy precast components. So it's a circular structure. The structure was conceived by Steve Jobs himself. He was big on promoting sustainable, construction. So he required that the floor slab has to have 3 functions. One, it should serve as a ceiling underneath it. So they don't want to suspend ceiling. Floor slab should be polished and shining in terms of, so Precast has actually brought in a special machine to polish each and every surface. On the top, it should act as a floor, basically, whatever the floor requirement was. And then in between, it was a cavity they used to heat and cool the campus as well. So the floor slab itself is a unique feature in this entire structure, and they had 4,400 of them. And typically for these structures, the precasters would go for something in the order of 3 to 10 millimeter tolerance. And I think Steve Jobs demanded that should be reduced to 1 millimeter. So, but unfortunately, he never lived to see the structure, but he was instrumental in terms of conceptualizing how the Apple campus should look like. So it's in Northern California, in a city called Cupertino. Pretty massive structure. I think his vision was that people should be able to see it from the space. That's what this circular nature of the structure. You kind of see that if you have an Apple phone, it kind of spins like that. Okay, I think that's my yeah, I think the structure has about it's at 4 floors on the top and 3 floors underground. So it's a total of 7 floors. The diameter of the structure is 461 meters. About 1,500 feet. Yeah, I think it's mine. So, yeah, again, when you see a structure, you don't realize it, but I think when a precaster comes in, they will figure it out as to how you want to do it. So the polishing requirement, so it's basically the bottom of the floor is marble, and plus it was polished. And there's no way the cast in place or any other means could have done it. So they precaster cast the pieces, and then they polish the surface to meet the expectation. Steve Jobs, I think, had a engineer on Apple campus, and so he was the one working with him in terms of conceptualizing the whole thing, and then they hired a design firm. So they had to sell the idea to the city first. We're going to build this campus, and Steve Jobs was nervous about people rejecting the idea, but the city said, yeah, you can build it. So, because of the electrical power requirements. But it's a massive, I think it was budgeted for $3 billion and ended up costing them $5 billion or something. But it's good to see that Precast was using the structure as well. Okay, so briefly, the takeaways is that total Precast system certainly offers speed, quality, and sustainability. Again, they don't just come with it. You have to work towards that, right? So there's an advantage with the precast fabrication, but you have to take advantage of it in terms of how you want to utilize it. Ideal for a wide range of building types. You could almost find almost any structure. I think one structure that I can go into details, I'll see if I can find some pictures, is stadium construction. We use precast in stadium construction quite a bit in the US. But it also has some limitations and special design requirements. So you got to engage the right people in terms of completing a successful design and construction of that building. Any questions? Everybody sleeping or what?